Hey guys, how's it going? This is another optimization tutorial, except this time we'll be optimizing a common 5 transistor op amp using parameterization instead of global variables, like my first video. I'm going to optimize this op amp for a DC gain of 30 decibels, which is not very high, but this is just a single stage structure, so it's fine. I'll optimize for a gain bandwidth product of 5 megahertz. I'll go ahead and add an expression for unity gain frequency as well. And since this is just a single stage structure, we should only be looking at one dominant pole. So the unity gain frequency and the gain bandwidth product should be pretty close. Here's my test bench here. We can take a look at it. VDD is 1.2. VSS is set to ground. My bias current is 10 microamps. My load capacitance is 10 picofarads. And then I have my common mode input voltage set to half of VDD, so 600 millivolts. And then I have this additional DC source here going to the negative terminal of the op amp. And the DC voltage is 0, but the AC magnitude is 1. This is for AC simulations that we're about to run. Now that we have our test bench configured, we can open up an ADXL worksheet. And to begin, we'll add a DC analysis. This is for the operating points of the transistors. And we'll also add an AC analysis so we can look at the DC gain and obtain the Bode plot, the Bode plot. So here we go, we're gonna simulate from 1 to 1 gigahertz. Leave everything else at default. Before we start adding expressions to the calculator, we need to run a simulation. Go ahead and press play. Alright, now that's done, we can go to the output setup, right click, add expression. And I have some expressions already typed here, but I'll start from scratch. First, we can go ahead and add expressions for DC gain. So I'll do VF, which stands for AC voltage. Click V out. And then for DC gain, we want to do dB20 because we want to be in decibels. And we're going to do value, and we're going to look at the second value, so interpolate at 2. Go and press OK. That will be your DC gain, so we can send that. Also, gain bandwidth. It's very easy. Click V out again and look for gain bandwidth. I'm in the function panel. I'm under all. Gain bandwidth product is right here. Click that, send that. Do the same thing for unity gain frequency. So over here, unity gain frequency. Send that one. I can also add an expression for phase margin right here, but since this is a one-stage op amp, I'm not really worried about stability right now. So that's it for the AC simulations. We can look at DC operating points for all these transistors here. 1, 2, 3, 4, 5, 6 transistors. Region, there we go. I want to make sure they're all in saturation. And instead of going back to each transistor and clicking, I'm just gonna type in 1, 2, 3, 4. Oh, actually, no, there's only 5. So T0 through T5. Also, I don't want the op amp to draw too much current, so I'm going to select the IDC, click the negative terminal of our power supply, and we'll send that to. I'm going to set that to a limit of like 100 microamps, whatever the spec calls for. Oh, and we want to be able to see our Bode plot. If I can do this real quick. F out 20, so it plots it in logarithmic scale. Go ahead and send that. And go to our output setup page, see all of our expressions here. I'm going to give our expressions new names, makes them easier to identify, and then I'll give our simulation results with specs. So for example, this is DC gain. This would be UGF. Gain into with product. Alright, that should be good enough. For the transistors, we want to be in saturation, so I'll do a tolerance specification. We'll do 2 because we want to be in saturation, which is region 2, and then I'll do a 1% tolerance. I'll basically just repeat that for all of them. Okay, that wraps those up. For DC gain, pretty sure I said I wanted 30 decibels, so we'll do maximize and we'll do 30. We can go here and play with the units, dB, give it 3 digits. Sounds good. Gain bandwidth product. We'll do maximize again, and we'll do 5 megahertz. Okay. And for the current restrictions, I'm not really worried, but for fun, I guess we can say less than 100 microamps. Alright, so now that our specs are set up, we can go ahead and run the simulation. And I haven't changed any of the transistor sizes, so the op amp probably isn't going to work. But just to show you what it looks like. Well, it's not too bad, I guess. We're almost at our at our spec. But yeah, there's definitely some improvement. We can double click here, see our Bodhi plot. So what that looks like, we'll verify our gain bandwidth product and DC gain at the end. Now we have to set up the parameters. So we can go over here to the drop down menu under parameters and click to add parameter. That'll take you back to your schematic, and this variables and parameter window should open. If it doesn't, you can go up here to window, assistant, and then make sure that this is checked, and then it'll pop up for you. Anyways, we're going to assume that our device is symmetric. So these PMOS transistors should have the same device sizes. So I'm going to press shift, and I'm going to click both of them. And I'm going to click right here on length, and I'm going to do match parameters, and it's basically going to set them equal to each other. Okay, I can do that for multiplicity and width. I'll do the same thing for the NMOS transistors. Set them equal to each other. And then the tail transistor is all by itself. So you can right click and do create parameter. Add all those and then go to T5 here. Do the exact same thing. And now we have this list of all of our parameters, and I'm gonna manually add a range for the optimization simulation to sweep. So for lengths, we can do something like 500 nano, and I'll step by 250 nano, and we'll go to 1.5 micro. I can copy and paste, I can do that for all the lengths. There we go. We can do the same thing with multipliers. I'll do 1, 2, 4, and 8. And then widths, I'll give them a little more of a range. We'll go to something like 8 micro. Sounds good. Setting this simulation up obviously depends on your maximum, minimum feature sizes. But look down the list, all of our parameters look good. Okay, so we can head back to our ADEXL, and all of our parameters pop up right here, just how they should. We can go ahead and close that tab. And now we can open up the local optimization. So click here, local optimization. Click here to add a reference point. I'll just do get schematic values. Load them for me, press OK. Everything looks good here. Pick whatever algorithm you want to use. I'll use the Brent Powell. And actually, I forgot in our output setups, we need to assign a weight for these. So I'm going to do that really quick. I'm going to give the transistor's operation regions 100 weight, and give our DC gain a weight of 80, and our gain bandwidth product a weight of 50. Just so that the optimizer has something to compare the specifications to. Go back to results and click play. I'm going to go ahead and skip through this because it might take a while because we have a lot of parameters. So the local optimization finished. We see our DC gain was within 10% of our spec. The gain bandwidth product was met. And we can verify this by looking at a Bode plot. Double click here. You can press H for a horizontal line. And our gain bandwidth product is about 5.7 megahertz. And our horizontal line is showing about 5.8. So it's pretty close. It could just be because my resolution for my AC simulation isn't set high enough. So that's no big deal. That's fine with me. If I wanted to make this a little better, I could go to up here and go to global optimization, which looks at a lot wider range of variables. It takes a lot longer. The local optimization simulation ran about 120 different simulations, but the global optimization might take, it might run thousands. Click here, right click, click back-annotate, press OK here, and if we go back to our schematic, it will update all of our device sizes. So now, instead of everything being defaulted, M is 8, etc., widths and lengths, 750. Then we'll also update our reference point. So right click again to create reference point. Now when we do our global optimization, it will start right where we left off. So I'll click play and I'll let this run for a while. Okay, so I'll let the global optimization run for about an hour, and our gain bandwidth product went up a little bit. DC gain went down just a little bit. It turned red because it dropped out of the 10% tolerance range. And we can look at our Bode plot, and it's very similar. Not a huge change. That pretty much wraps this up. Thanks for watching. I hope you learned something. If you want to, please comment, subscribe. I'd really appreciate it. Thanks. Have a good one.